गुड मॉर्निंग, मैं विकास पांडे। आज इंट्रोडक्शन टू पावर क्वालिटी में ट्रांसफार्मर, मैग्नेटाइजेशन एंड नॉन लीनियरिटी पे डिस्कशन करेंगे। इंट्रोडक्शन टू पावर क्वालिटी। टॉपिक इज ट्रांसफार्मर, magnetization and non-linearities. The magnet circuit is one of the most important active part of the transformer. It consists of laminated iron core and carrier flux linked to winding. The magnetic circuit the magnetic circuit the magnetic circuit is one of the most important active parts of transformer. It consists of laminated iron core and carries flux linked to winding, flux connected to winding. Energy is transferred from one electrical circuit to another electrical circuit. One electrical circuit to another through the magnetic field. To the to another through the magnetic circuit. Field carried by the core. The performance of transformer is very good for ferromagnetic core transformer. For ferromagnetic core transformer, we must be mindful of the saturation limits of the core. There are several methods are used: harmonic phenomena and core saturation. Then harmonic phenomena and core saturation. First point is harmonic phenomena. The non-linear magnetic characteristics. The non-linear magnetic characteristics of the transformer core are needed to predict distortion of its primary current. One of the method of estimating harmonic load content is percentage of percent total harmonic distortion percentage total harmonic distortion. The percentage total harmonic distortion can be defined in two different ways. As a percentage of fundamental component, as a percentage of the fundamental component that is IEEE definition of total harmonic distortion component, or as a percentage of the RMS. The percentage current total harmonic distortion is the percentage current total harmonic distortion is, then total harmonic distortion is equal to under root summation of k equal to 1 to infinite ki IK square RMS upon IRMS multiplication of 100. When IKRMS is the amplitude of harmonic component, when where IKRMS is the amplitude of the harmonic component of order K, that is the kth harmonic, and IRMS is the RMS value of all the harmonic that can be represented as IRMS equal to under root summation of h equal to 1 to infinite IK or IH square RMS. Equation number 2. This is equation number 1 and this is equation number 2. The total power factor is power factor equal to P upon V1 RMS into I1 RMS under root 1 plus THD I upon 100% square. Equation number 3. The total power factor is sometimes called a true power factor, as shown in equation number 3. The total power factor is the product two components. The first component is called a displacement power factor. The first component is called the displacement power factor, that is df IP equal to P upon V1 RMS into I1 RMS. This is equation number 4. The second component of total power factor is called distortion power factor, and the harmonic component of the current is PF DIST equal to 1 upon 1 plus TSD I upon 100% This is equation number 5. If the voltage across the harmonic component, if the voltage also has harmonic components, then the distortion power factor would be product of two terms, product of two terms like the right side of equation number 6 the right side of equation 6, one for voltage and one for current, one for voltage and one for current, then PF dist is equal to 1 upon under root 1 plus TSDI upon 100%. Multiplication of, it is the multiplication of two terms or two component, equation 4 and 5, then 1 upon 1 plus TSDI upon dV upon 100%. Equation number 6. However, we normally expect the voltage distortion to be very low compared to the current distortion. However, we normally expect the voltage distortion to be very low compared to the current distortion. Second point is core saturation. A typical hysteresis loop of soft magnetic material is shown in figure 1. Then figure is minus H. This is minus BS, the BS, B positive, B negative, 0, minus of SC, minus of BR, HS. Typically BH curve of the soft magnetic material. In figure 1, in figure 1, the hysteresis loop clearly shows the flux density BR the flux is polarized flux remaining in the core. The flux is the polarized flux remaining in the core after the excitation has been removed. The magnetization force minus SC is called correctivity. It is amount of magnetization force. It is the amount of magnetizing force required to bring the remains flux density back to zero. And third point is permeability. The permeability of magnetic material is measure of the erase the magnetization of the material permeability. Mu is the mu equal to B upon H, where mu is the ratio of the flux density B to the magnetizing force. The relation between B and H is not clear. As shown in figure, the figure is B or H Bs magnetizing force permeability. The relation between B and H is not clear. B and H is not clear as shown in the hysteresis loop in figure 1. The variation of permeability with flux density. The variation of permeability with flux density B is shown in figure 2. This is the figure 2. Also shows the flux density at which the permeability is at a maximum, and relation between HPK is equal to 2HS. By definition, saturation occurs the peak excitation current B is twice of. By definition, saturation occurs when the peak exciting current B is twice the average exciting current A as shown in figure 3. Then figure is IM T then figure is IM T time magnetizing current 0. This is B, this is A, and time. Saturation occurs when B equal to 2. Okay, thank you very much.